We've been studying eigenvectors and eigenvalues. So the definition is that an eigenvector is a special vector that when you multiply it with a matrix, it will just end up being stretched. If we're in an eigenvector basis, working with A becomes really easy. And a little bit more precisely is that it becomes very similar to working with a diagonal matrix. So if we want to see this a bit more clearly, we have to use this basis representation. And that means if I give you an eigenvector basis, so if I have a matrix n by n, and if it has an eigenvector basis, that means I have n linearly independent vectors, they're eigenvectors. What I can then do is take any vector and write it in its basis representation. We've already talked about this idea of coordinates, and then the coordinates are just the weights of each basis vector. Now, I can extend this. If I were to take that result and multiply it by the matrix A, this is where the power and the usefulness of those eigenvectors comes in. I can go ahead like this. I can apply linearity, and I will be able to come up with a new set of coordinates. Now, the point of doing all of this is, again, these eigenvectors are here. This is going to give me lambda 1, v1, all the way down to cn lambda n vn. Now, if I ask you for the basis, the vector, eigenvector basis representation of this, I've got it right there. So the coordinates here end up being the weights in front of each basis vector. C1 lambda 1, Cn lambda n. Now, here is the key point. That vector could be obtained by taking this diagonal matrix and multiplying it by those weights. This matrix D is formed by putting the eigenvalues down the diagonal, and this vector is just the coordinates of that original vector. So the point of the story here, this is the key understanding, that when you look at it in eigenvector basis, all you are doing is just multiplication by a diagonal. So when we are in this B basis, AX is like D multiplied with this vector. And that is the whole point. That is why we are doing all of this stuff. We are tilting our head to put ourselves in the right language, in the right basis, in the right orientation, in the right set of coordinates, so that the matrix I'm working with in my problem is really, really easy to work with. Now we're going to formalize this idea with a new concept, and it uses change of basis. We're going to start with the vector x, and it's generally going to be given in standard basis, because typically our brains are wired to give everything in standard basis, and yeah, ultimately we want to get to some ax. We could just do it directly, but that wouldn't be taking advantage of this concept of eigenvectors. What we are going to do is, first of all, we are going to change basis to eigenvector basis. So that vector, we're going to change its name to xb. Once we are in that basis, then we are going to apply the transformation. Now, the advantage of doing this is that the name of that transformation is just a diagonal times the coordinates there, and then we're going to change back. So we're going to change our basis back to standard. So in step 1, we convert to this B, the eigenvector basis. So we take our vector, and we know how to write it as a basis representation. Earlier in the course, we discovered that this is the definition of a matrix times a vector. These are the eigenvectors. So we're going to call this matrix P, and we know that that column there is the coordinate representation. Now, since that matrix P is made up of a basis, it means that the matrix is invertible. So if I want, I could represent things like this. I could say that the coordinates there are just P inverse times X. And that's what I want. I want the name of my vector in terms of this new basis. Well, now I'm going to apply this transformation. I'm going to apply A, which I can think of as a transformation. And I know that when I do this, I'm going to be starting from my vector in this coordinate system, and I'm going to turn it into this vector in that same coordinate system. Now I'm in this language. So in this case, I already know what this is going to be. It's just going to be a diagonal matrix times that. So another way to think of it is I am taking that D and I'm multiplying it by the answer I got above here. And now I will be able to write this as D times this P inverse X. So that is the name relative to what I started with of that point in the story. And then that third stage going down, I want to change to standard basis. Now here's a little note, right? Above, we said that if you have some vector, this is how it connects to its coordinate representation. So if the vector that I want is AX, then it should just be this change of basis back, and then I would put this AX in there. Well, I'm now going to take this result, put it in right there, and I will come up with this final representation. I'll have P, D, P inverse times X. Now, another way to put all of this is that these X's are the same, so I have just found another way to represent A. This is a different factorization of this matrix A. Now, this factorization is special. It has a diagonal matrix in the middle. We are going to call this a diagonalization of A. A, which is an n by n matrix, is said to be diagonalizable if there exists some invertible matrix P, and that has to be a square matrix by definition of invertible, and a diagonal matrix D such that A equals P, D, P inverse. The discussion I did above kind of also gives us another immediate result, and this is proposition 4.3.3. So this matrix A, which is n by n, is diagonalizable if and only if columns of P are eigenvectors of A, and the diagonal matrix has entries, and the diagonal entries of D are the corresponding eigenvalues of A. If you want to be able to write this, P has to hold your eigenvectors, and D has to hold the eigenvalues that correspond to those eigenvectors. And remember, in a diagonal matrix, there are zeros everywhere. It also means that if you ever are able to somehow write your matrix in this factorization, it means that the only way for you to be able to do this is if your entries of P and D are eigenvectors and values. Now we know that if you have n distinct eigenvalues, this is always diagonalizable. That's great. If we have repeated eigenvalues, you're only going to be diagonalizable if the sum of all the dimensions of all the eigenspaces equals n. So, to try to put this a little bit more concretely, here's this matrix that we've been dealing with before. It's a 2 by 2 matrix. I would like to find a diagonalization of it. Okay, well, I know one eigenvalue, and I know one eigenvector. I know another eigenvalue, and I know another eigenvector. Again, it's pretty straightforward for you to be able to sit there and compute this. So, one option here for V is for you to sit there and put these two things in that matrix, and here's the other option for, or here's the option for D. And if you choose that, yes, A will be able to be diagonalizable. You'll be able to write it like this. Now, if you want, you could sit there and verify it. You could say, all right, there's P. P is 1, negative 1, 1, 1. You could find P inverse. You'd get a half as the 1 over the determinant, and P inverse would end up looking like this. And then you could sit there and compute P, D, P inverse, and you could find that it will equal your original matrix. You don't need to do that. Diagonalizations are not unique. There isn't just one diagonalization of your matrix. If you felt like it, you could have put the vectors in the other order. That's okay. All that you would have to do is adjust the eigenvalues to match. This is an example we did last time. This matrix has a repeated eigenvalue. You could either redo this yourself, but what we found in the previous video is that, okay, there's the eigenvector for this. The dimension of the eigenspace corresponding to this lambda is 1 because there's only one eigenvector basis here. This thing, we found that it had 2 eigenvectors, and they were linearly independent. We also found that there was a theorem that we talked about last time that said that any vectors that come from different distinct eigenvalues have to be independent of each other because these two form a basis. They are independent of themselves, so the whole mess is independent. And yes, in this case, you will be able to diagonalize the matrix. You will be able to write it in this form. You will be able to apply the matrix as if it's diagonal. You could write V1, V2, and V3, and you could choose your diagonal matrix to be 1, 2, 2 with a bunch of zeros everywhere else. Not every matrix is diagonalizable. This matrix has a repeated eigenvalue of 4, but there's only one eigenvector. So the dimension of the eigenspace here, E4, is 1. This vector doesn't have enough this matrix doesn't have enough eigenvectors. It's not diagonalizable. You're probably saying, so what? Who cares? Why do I care about all of this stuff? What's the point? Okay. Again, the main consideration here is that we want to apply A as if it were a diagonal matrix. It allows us to simplify certain calculations. As a simple example let's say I give you a matrix like this. So let's say I have 1.1, 0.9, 0.6, 1.4. I can show that, yes, there's an eigenvalue of 2 and an eigenvector of 2/3 and 1. There's another eigenvalue of 1/2, and its eigenvector would be -1 and 1. I would like to know, let's say, a to the power of n, because I'm looking ahead to dynamical systems, and that's where we're going to talk about in the future. We want n to get really big. So I don't want to necessarily sit there and compute a matrix product over and over and over again. So diagonalizability will help. So A is diagonalizable here. It has enough eigenvectors. If I now wanted to exploit that and say, look, let's compute A squared. Here's what you could do. You could say, look, when I have a bunch of matrices like this, I'm allowed to insert brackets wherever I'd like. So I'm going to choose to insert a bracket here. Then I'll get a P, D, D, P inverse. And that is a P, D squared, P inverse. So I'm going to take a little bit of liberty here and say, look, if you just kept repeating this over and over again, you'd end up with something like this. You say, well, that's horrible, right? This doesn't look much better. I still got to raise this thing to a power of n. That's awful. But it's diagonal. And because it's diagonal, your life is better. If I were to say to you d squared, look, I'm going to show you a very simple example here. Let's just take a 2x2 case. If I were to write this matrix and just do the matrix multiplication, you're going to find that this is what will end up happening. All you have to do is square the diagonal entries. So if, again, you generalize this, if you ever have a diagonal matrix, all that will end up happening is that you have to just raise the diagonals to that right value. In our example, we would have P, we would have this 2 to the n, 0, 1/2 to the n with a P inverse. Now, in the long term, we're talking about n going to infinity. So in the long term, when n goes to infinity, you can start to see what's going to happen to this matrix. Oh, that term's going to eventually go to 0. And all I'm really going to be left with is a contribution from this. And that is kind of the backbone of how we use this stuff to study dynamical systems.